for coming. We have a couple of people in attendance. Let me just provide a brief introduction. Today's talk by Dr. Zhijun Qiao is on integrable systems with Peakons and Cuspons. Dr. Qiao is currently the presidential professor at University of Texas, Rio Grande Valley. Before that, so he got his PhD at University, and on his way to Texas, Rio Grande, he's also been at a number of other institutions, including an Alexander Humboldt research fellowship, which was used in Germany, I believe, at the University of Kassel. As I said, today he's going to talk to us about integral systems with Peakons and Cuspons. Thank you, Professor Qiao.
Okay, thank you, Bernard, for your introduction. Let me. There's some noise. Okay, great.
So can you press Ctrl L on your machine to maximize the slides?
Yes, let me maximize slides.
Great.
Full screen mode.
Great.
Now it's better?
Yes.
Okay. All right. So can I go ahead right now?
Please. Go ahead.
Okay. Hello, everybody. Very nice to meet you and talk to something regarding integrable systems and recently development in Peakons and Cuspon. Okay. So here's the integrable systems with Peakons and Cuspon. Before I start my topic, let me introduce my group member and the student. It looks like the echo series. If I can you hear or not?
Yes.
Let me try. This is audio. No, I think I should keep audio on. Otherwise, you cannot hear me. Okay. Okay. Anyway, so currently we have 3 faculties in our group. One of them is doing nonlinear Schrodinger equation and nonlinear optics. The other one is Wesley. He's doing some signal processing in the inverse problem. And listed those are scholars. They are coming from China, most of them. Some of them doing integral systems in solid solution. Some of them they are doing the big data analysis and signal processing. So basically, in my group, there are 2 directions we work on. One is nonlinear integral system solid solutions, and the other one is inverse problem. Equation in image processing and signal processing. The last 2 lines listed our PhD students and the master students. Okay. And here our current research programs, let you guys know. First 2 regarding inverse problem. The model we worked on before is Maxwell equation. That's the foundation for the inverse scattering transform and inverse scattering for the radar imaging. Okay. So the application for the Maxwell equation, is electromagnetic waves. We use the, usually it's called Fourier transform.
But for SAR, so synthetic aperture radar signal processing or image reconstruction, we use the Fourier integrable operator. Okay, application. One of the things is compressive sensing, sparsity fitting, and a 3D moving target image reconstruction. That's the one of research area currently we do. The other one, this is our how to remove that. Okay, I moved that there. Okay. The other is currently so very hot topic is the integrable dynamical system with wicks. There's a Peakon, Cuspon, and other type of solution like a king. But I listed here is currently we are keep tracking those open problems or frontier research directions. One of them is higher dimensional Peakons. For one dimension Peakons, Camassa-Holm equation, EP equation, we worked out so much. But for higher dimensional Peakon model, we know a little bit. Second point is discrete integrable Peakon system. So people know the KdV equation. And the KdV equation does have the discrete version. Now we know the Camassa-Holm equation. The natural question, how do we develop a discrete version for Camassa-Holm equation, particular for discrete Peakon system? That is still open. We don't know. This is quite interesting, important for the Peakon theory. The third part is for analysis. Now the one dimensional integral Peakon system, many analysis worked before. But for high dimensional Peakon system, we don't know much about analysis work. Okay. The fourth part is eigenvalue problems. Remember, Lux theory is composed of two parts. One of them is eigenvalue problem. The other part is time part. So spatial part is eigenvalue problem. In the past, it's a Sturm-Liouville eigenvalue problem. It's the second order eigenvalue problem. But for Peakon system recently, we know there's a third order eigenvalue problem, but that part we know a little bit. So question, how do we figure out the eigenvalue distribution for the third order eigenvalue problem? We don't know much about it, okay? For our research, you can take a look at my website in ResearchGate if you use ResearchGate. Okay, now let's go to outline. So here's my talk outline. For background for Camassa-Holm system, then I'm going to show you how do we derive single Peakons, Cuspons, and small solitons. So for second part, probably Hohan, when he was a master student here, I showed him how to derive Peakons and Cuspons, okay? The third part is the Camassa-Holm spectral problem and hierarchy. And then I'm going to show you integrability. So here integrability, which means in the sense of last part. Okay, so last part give you conclusions. Okay, let's see the fundamentals for the so I just a quick review for that part. But since you guys know KdV very well, okay. So basically, for KdV equation, it has such kind of a Bell type such square travelling solution. This is a permanent form travelling setting. You plug in there, students can do the integral and use a calculus or either software get an explicit solution. But the important thing is this solution is stable for the integrable equation, but not for non-integrable equation. Usually, we don't know much about it. Okay? The interesting thing is such two soliton interactions before interaction and after interaction, they keep a original shape. This is why KdV solitons is important. Even for unsolitons, keep the same property. So in the literature, there's some two concepts. One is solitary, the other is solitons.
In mathematics, if this equation is integrable, then such kind of traveling wave solitary wave solution we called solitone. If you don't know the system is not integrable, what you didn't find any last pair, well, you specifically called a solitary wave solution. That's just like Bell type. Okay, that's also we need to clarify. Now this page showed you peaked solitone and Cuspon. So peaked, which means peaked solitone. If you use a math language to describe a peaked solitone, which means at the peak point, not smooth. The solution is continuous. But at the peak point, both left derivative and right derivative both exist but not equal. So simply say the solitone-like solution at the peak point and has the final jump for its first order derivative. That's what we call Peakon. Now, second concept is Cuspon. So compare with is more deeper or most deep than Peakon. You know, so use math language to describe the property of the point, which means the first order derivative at the Peakon point is infinite. Peakon simply has a finite first order derivative. The Cuspon is infinite express point. Is that okay, guys? There.
Yeah.
Okay, good. So otherwise, I can slow down my speed because there is some voice probably is not so good.
It's okay.
It's okay. All right. Okay. I go ahead. So integrable, which means that in the sense of Lax pair, you know, so for nonlinear differential equation, if you find two linear problems which compatible condition nonlinear differential equation, that is called the Lax pair. So in the pair, the first part is eigenvalue problem. Second part is time part. Then in my talk, I'm going to show you how to get a Peakon and then later on, if I have, I'm going to show you how to find a Lax pair. So finally, the last step is final step is open problems. Okay. Let's go to the Camassa-Holm system. That is the first Peakon system in the literature. Okay. This is a well-known paper for the CH Peakon, the published PRE in 1993. So this is the system. It's already simplified without any physical parameters. So here's number 2. Usually in the this part, U is a particle velocity, M called filtered velocity by calculator. So usually, before you double it, there is a parameter alpha square. But if alpha square not equal 0, always you can simplify the form like this. Okay, this is simplest form for Camassa-Holm equation. So this describes the unidirectional propagation for shallow water. This is still for shallow water. Okay. Now the last pair was followed by mathematician. Also here's pair. This is time. This is spatial part. Eigenvalue. This is a little bit different from the Sturm-Liouville eigenvalue problem. Be careful. The lambda is eigenvalue parameter. So also the psi is the eigenfunction. M is dead end. It's called potential function. And this is the time part. Okay. If you look at the time part, very different from the typical integrable system. Here includes lambda reciprocal. So which means, so CH equation would be in the negative power of the eigenvalue direction. So in the integrable system, actually, so CH equation is coming from negative flows of the hierarchy. I'm going to show you that later on. Show you why is CH in the integrable a negative flow. So I put a question here, and this is most likely for the Sturm-Liouville eigenvalue problem equivalent question. If M is better, what is the distribution for lambda? Okay. So since the Camassa-Holm work, 1993, there's a bunch of the purely mathematicians work on that system. So I listed some representatives: the famous mathematician Konstantin Makin, Bill Settinger, Simginsky, Johnson, Asher, Himonas. I think Himonas would be in the Athens conference. I saw, Bernardo, you're gonna go there, right?
Yes.
Okay, I'm going there too. Okay. This is the Guo, one of Chinese guy. This is the Zhao Yangyin. This is the Yu Liu. Yu Liu, the Bernardo also know him probably. Yu Liu. David Liu. Okay. That's myself. So today's some work is based on my 2003 paper. It's regarding Camassa hierarchy and I do think I have time to talk about the pure math work regarding algebra geometry solutions. Okay.
Can I ask a question?
Okay. Sure. Go ahead.
In your form of the Camassa-Holm equation, so often there is there's an extra term where you have a parameter times ux if you write everything in terms of u. So in your formulation, that term is missing.
Oh, which one?
So it's the term that. So I think if you set the coefficient of the term equal to 0, you get Peakons, and otherwise you don't. So you were restricted to the Peakon shape?
Right. So if a Peakon, so for this equation, some people put a linear term for this one. For the linear term, like some parameter times u sub x.
Yes, correct.
Okay. If for that part, if you think about the Peakon solution, the decay at both infinities, there's no linear term, which means a linear term, the coefficient must be 0. Otherwise, Camassa-Holm has there's a regular soliton and a Cuspon soliton. I'm going to show you later on about those other two kinds of solutions. So good property for Camassa-Holm equation, it has 3 kinds of different solutions. So Peakon solution, Cuspon solution, and a regular soliton solution as well. Is that address your question?
Yes, thank you.
Okay, no problem. Okay, can I continue?
Yes.
Okay, all right. So let's see why is the Camassa-Holm equation is important in the literature. One of the issues that could be derived from Navier-Stokes. Hello? Any question?
No, go ahead.
Oh, okay. All right, sorry. So this is a typical Navier-Stokes equation in 3-dimensional. So V is velocity, the take derivative is acceleration. That term is convection term, nonlinear term. P is pressure, nu is viscosity constant. That is external force. So this stands for the flow is incompressible. Okay. Of course, this is a $1 million problems. Okay, for 3D. Of course, this is very hard. And one of the issues to study that equation when I was in Los Alamos, so my first stop in U.S. There's a 2001 through 2004. Their Holmes working group, the put V equals this kind of, we call it Helmholtz operator, acts on the velocity u. Here's alpha is parameter, beta is Laplace operator. So this is called filtered velocity u. Then plugging into the equation 1 and 2, you get a following model. This is their home group called NS alpha model. Okay, NS alpha model. So you have 2 nonlinear terms. So P is still pressure, V is viscosity constant. The key is the original. Now, this is compare the original Navier-Stokes equation a little bit maybe complicated, but it's called, this U is called Euler fluid velocity, but filter. Okay, velocity, yes. Okay, let's consider a special case. If nu is 0, p is 0, f is 0, then it's also 1 plus 1 dimensional case. That's 1 times 1 spatial variable. they'll exactly get Camassa equation from Navier-Stokes alpha model. Okay. In the past, some people ask me regarding what about high-dimensional Camassa-Holm model? You know, so basically, from a background of a Navier-Stokes alpha model, I think we should starting from this model 4 to derive high dimensional, like 1 plus 2 dimensional Camassa-Holm. Okay, but unfortunately, from there, if you think about 1 plus 2 dimensional model, most likely is not keep the integral. In other words, the Lux pair probably is not exist at all. So this is somehow we need to do in the future for high dimensional Peakon system, starting from an alpha model. Okay, this is the simple background for the Camassa-Holm model. Now let's go to the Peakon solutions. The Peakon solution, of course, is kind of traveling wave solutions. Okay, so let's put a traveling setting. You plug in the PDE, then PDE comes to ODE. Then just regroup. You have this very good formulation. Okay, be careful. C is wave speed. Okay, this ODE. How do you get a Peakon solution? I directly write down from this equation to this function. This UXT satisfies that equation. But the question is, here I got absolute value x minus ct, and here's wave speed. This c must be same as this c, this same. Okay, let me tell you a little bit more detail about the idea how to get this solution. This is, it's a very simple function, right? Okay, so now actually it's a special solution from this equation. First of all, of course, any constant is a solution of this equation. That's trivial. We do care about it. Now, second, what about other special solution? Very specifically, it's what? F minus F double prime equals 0. If F minus F double prime equals 0, if I write on the screen, can you see my handwriting?
Yes. Yes.
Okay, great. Let me write down there. So look at F minus F double prime equals 0. Now, what is general solution? Exponential psi, exponential minus psi, right? That's I put C1, C2. That's a general solution for the very simple ODE, but nothing to do with that. However, if you draw the graph e to the psi and draw graph of the e to the negative psi, then cross each other, you find what? Cut off the upper part, or keep the lower part. What is this? That exactly exponential minus absolute value. Okay. Now, question is, those smooth point, no problems, satisfy that equation. The only thing is at the crest, that's a Peakon point. How do we verify that equation? So, for the absolute value in a typical calculus, you cannot take the derivative because at the peak point, no derivative exists at all. Now, question: how do we verify that function is a solution of that equation? So that is no longer in classical sense. You need to do in the distribution sense, verify this function is a solution in that equation. Okay, that's why pure mathematicians work on the Peakon solution in analysis. Okay, so let's look at the picture of e to the negative side. Let's go to infinity. Now, the next picture show you something like this. So you see at the peak point, there's both left derivative and the right derivative exist, but they are not equal. Okay, that's a Peakon solution. So remember, how did you get a Peakon solution? You consider very specific case. You ask question?
No.
Okay, all right. Let me continue. So very special case, you put the F minus F double prime equals 0, you get a Peakon solution. Now, general question: what about
f minus f double prime is not zero, what kind of solution you get? This is our work in 2006 with my collaborator Guoping Zhang. That is the when Houhan was here, I let Houhan work on that paper 2006. You know, he derived some solution from my notes. Okay, let me see the Cuspon solutions here. So this is I skip the procedure how to derive it. There's a long procedure, and then use some strategy to get explicit solution like this. Okay, but again, you consider f minus f double prime not zero, you get this kind of solution. So let's analyze a little bit. So the asymptotic behavior. So when you know, so Xi goes to infinity, plus or minus infinity, this of course no longer goes to non-zero constant. This goes to number a. What is a? A is 3 times wave speed. Okay. Now what about Xi equals 0? Xi equals 0, of course this part is going to infinity, so that's just a c. And at 0, the both left derivative and right derivative do not exist, which means in this case the derivative has infinity term. So this is Cuspon solution. It's different from regular, or different from Peakon solution. So careful. In this case, the boundary at infinity is non-zero. Okay. Now draw the picture. You see, when x goes to minus infinity goes to 3, positive infinity goes to 3. So this is the proportion in this amplitude in the wave speed. Okay. Okay. This is the Cuspon. Of course, we can also get smooth solitons. The smooth solitons are very different from the PDD equation. So this is we derived the secant square arc cos and secant hyperbolic secant. Okay. This case, you know, is the amplitude is at both infinities. This goes to the other constant 3 over 11. Okay, but those are the smooth functions. You can draw a picture, something like that. Okay, now question is about in what case you get smooth solitons, in what case you get Peakon, in what case you get Cuspons. For Peakons, for the standard Camassa-Holm equation, as long as the boundary at infinity is 0, that's Peakon. Now, for what case you get smooth soliton and Cuspon, you need to analyze the ratio between your boundary and we give the analysis work much detail in that paper if you want to know details. Okay, there's a ratio between your boundary and wave. Okay. Okay. This is the single traveling wave solution Cuspon in speed. Okay. Now let's go to multi. Now people ask Cuspon. What about multi-smooth solid CH equation? In the literature already did. If you take a look at one of Chinese in 2006, published in the proceeding of the Royal Society, they look at this paper already. Now, for the multiple Peakon solution, is provided by Camassa-Holm in their original paper. This is an ansatz, very important to work on the Peakon solution. So still, the strategy is what? Put that ansatz to reduce the PD to ODE system. That is strategy. Okay. Now plug the UXT into the equation, work on the computation to get the following system. That's a 2-unknown equation. In this equation, in this system, no x involved because x is there. Plugging there, you just get ODE system. Now question, how do we solve this ODE system? They're still nonlinear. It's because you have absolute value there. You have the sine function there. Okay. Now,
In integrable system, first of all, because that's the ODE system, we first focus on how do we verify the integrability for this ODE system. That's the typical Liouville-Arnold theory. Okay, so first step, we're gonna rewrite that ODE system into canonical Hamiltonian structure. So this is Camassa-Holm work. So H is very good formulation. Okay, this is Hamiltonian, but it's in the absolute value form. Now question, well, that system is very integrable, so we have to find finite number of conformation laws because this is a finite integrable system. So finite 2n system. We need to find n number of conservation laws which are independent. Then that system is integrable. So now the work done by Degasperis-Procesi in 1996 published physical thing. So rewrite that Hamiltonian system under an assumption there's a Peakon position, Q1, Q2, Qn. Can remove the absolute value, you get this canonical equation. Okay. So Ragnick and Borsky found a Lux pair for this OD system. So now it's M and L two matrices. So L is a symmetric. You see here, this is a diagonal element. Sub-J stands for it's a diagonal basis. Okay, so PJ is diagonal elements. So this is stands for here plus, and that's symmetric. But M is antisymmetric because it's a minus. Its diagonal is 0. This is the matrices make the commutator on the right-hand side. So left-hand side is a derivative with respect to time t. So that is the matrix Lux pair equivalent to above the canonical Hamiltonian system. Okay. Then after you get Lux pair, now of course we can get infinitely many conservation laws. That's typically we need to work on Lux pair. Why is Lux pair important? So just take Lux matrix, the power, and the take trace, the take derivative respect to t, that equals 0. You just count the first n, you get the n conservation laws. Okay. Now verify that's the integrable systems in the Liouville space. Okay. That's the quantitative analysis. Now, what about the two dynamicals for the two Peakon solutions? Can you give me the exact solutions? No, it's Camassa-Holm. They compute the following two Peakon systems. So you have two, because C is a wave speed, let's suppose you have two wave speeds, C1 and C2. C1 is greater than 0. Now the two Hamiltonians, one is H1 and the other is H2. So the right-hand side is constant, okay, because conserved. Now you take the Hamiltonian, canonical Hamiltonian system, you have such formulations, okay? So you solve those P1, P2, Q1, Q2. This is the Camassa-Holm solution, okay? I just listed here. They give a solution like this. Q1 minus Q2 is something like this is explicit form. Okay, P1 minus Q2 is this. C1 and C2 are constant. Okay, the last two, the plus minus, you get P1, P2 solved. Now plug in the Q1 minus Q2 in the first and second equation, take integral, you get Q1, Q2. Now after that, don't forget plugging back your original ansatz, this form, capital N equals 2. Now you've got the explicit solution for two Peakon systems. Okay, I draw the graph here. Okay, so one is anti-Peakon, then upper. So active is negative, the part is positive. I didn't plot the animation. Of course, you can use MATLAB for the animation because this is already the exact solution. Okay, this is two Peakon. Can we work on this three Peakon? Of course. Yeah, just the students use some strategy to compute. Okay. All right. Let me see what time. Okay. So I was supposed to have another 20 minutes, right?
Correct.
Okay. All right. This is the first Peakon is Camassa-Holm equation. Now let's work on the second Peakon, or even more Peakon stuff. There's a Camassa-Holm is number 2. Look at equation 12. Now is here the 6 years later, the Degasperis-Procesi, they proposed this equation. Now currently we call DP equation. So just change number to 2, 3. Their paper very interesting. They published a paper in Proceeding, not regular journal. No, because in that year they didn't know the physical background of that equation. So later on, so Adrian Constantin and other mathematicians found that equation could be derived from Euler water system. Okay, so change to 3, they found this equation passes Pahlavi basis. Okay, that equation is integral. It still has a Lax pair. Most important is this equation still has Peakon solution. Okay. Then 3 years later, Holm and his master students, they changed the 3 to arbitrary constant B. There's people now called B family. So B family is still has the Peakon solution. In other words, actually, the Peakon solution for that nonlinear term really doesn't affect much. So only the first 2 terms affect. Okay. So for the integrable system, it's only B equals 2 and B equals 3. They prove the B family, has in the integrable systems for only 2 cases. So for B equals 2, that's a second order eigenvalue problem. Now B equals 3, so those are 3 people, Degasperis-Holm and Holm, they found a Lax pair. That's a third eigenvalue problem. That's the first part. The second part is you see here's a lambda reciprocal. So from the second part you see that could be derived from negative flows of the DP equation. This is why I worked the DP hierarchy 2004. So they published the 2002. That I worked on the 2004 for the whole hierarchy in negative of the DP equation. Okay. Now the question for the equation number 14. This is third eigenvalue problem. Now what about the lambda's distribution for third eigenvalue problem? We don't know yet. All right. So there's a for quadratic formulation to have the Peakon. There's the quadratic nonlinearity, and it's changing the parameter. So now going further, what about the cubic model? Okay. So that's a 2002 story. Find the B family. Now 4 years later, myself worked on that equation. Now currently people call it a fork equation or modified Camassa is this equation. This is the first cubic Peakon model. So interesting thing, so when I worked in 2006, I didn't notice the forecast in over Rossner 95 and 96 work. Yeah. So later on, I found that equation is could be included in their paper as a set of some special parameters in their systems. But I put the cubic needful. My original point is can we find Peakon solution for this cubic system? Okay, actually, this cubic is still integrable and a Peakon type solution. That's why so from 96 to 2006, no people focus on that equation. Since my work, now many people work on the Peakon and multi-Peakon and even analysis work. Okay, that's at least the Peakon for their Lax pair. This is the Lax pair eigenvalue problem, and this is the time part. You see the time part, not only lambda reciprocal -1. There's -2 there. So that has to be a negative flow. So this is the compatibility give you the Lax pairs condition produce this cubic equation. Okay. Now question is how about lambda distribution for that eigenvalue problem? We don't know yet. Okay. Now, so negative flow, you have the Peakon solution. Now, what about positive? The positive part of that cubic equation, this equation. This is somehow another integrable equation. Okay. Okay, that's the 2007 paper. Now, it's after several years, well, now the put cubic, quadratic, and linear terms together. That is my postdoc, Professor Xia. Also studied that system. We together find more interesting things, the solution, Peakon solution in Degasperis. Okay, this is the Cuspon solution for this system. When B equals B is non-zero. Okay. Now let me show you the Degasperis for this equation. Oh, I'm sorry. Here is the equation. This one, 20. Okay. That is still integrable. This system is just like a Gardner linear combination of the KdV and MKdV and some linear term. Now here with Camassa-Holm and cubic Camassa-Holm, that's combination. Now what is Degasperis? Degasperis I showed here. So spatial part, time part. For spatial part, a little bit complicated, but still traceless. You see here minus alpha and alpha. This is the time part. Okay. Now for alpha, it's a little bit different from the previous eigenvalue problem. So the eigenvalue, the square root of something. Now B is linear. If B non-zero, you require lambda, must satisfy some conditions, such as alpha is a real number. Okay, ABC now you have negative power there. Okay? That would be in the negative of the integrable system. Okay. Now this is the curvature condition, which is Degasperis form, so give you generalized equation. And so on and so forth. That's the combination of the Camassa-Holm and cubic. So the number 6 is another Peakon model called two-component Camassa-Holm. Okay, so I want to skip that part because I just introduced, cubic model is Novick model. Probably your group people also know that model. This is important, but it's the 3x3 eigenvalue problem. Okay, a related system is a two-component Novikov system in such more the Peakon system. Just I listed the model there. All of the Peakon system here are integrable. Okay, except two component. So that doesn't have Degasperis yet. Okay. Other Peakon model, that's my postdoc worked with me several years ago. I also listed the references here, just in case you want to know model, work on the other stuff like analysis or application problem. At least some questions here. High order Camassa-Holm equation. Here is high order, which means derivatives, not a nonlinearity term. Now the generalized Peakon model from the nonlinearity term is the cubic, quadratic. Now even higher order nonlinearity we don't know, but here high order, which means high order derivative. Okay. And a high order Novikov equation and high order modified Camassa-Holm equation. That is for future work. Okay, let's go to my third part. Is the spectral problem. I only have 10 minutes left. Let me finish this part. That is a Camassa-Holm spectral in Camassa-Holm hierarchy. So our starting point is from the eigenvalue problem. Okay, this is the eigenvalue problem, or this is would be 33. I should not try. The number would be constant. That of course changes the matrix form. Our goal is to find the square eigenfunction such that the eigen squared function satisfies this formulation. This is a very important key to out the two operators K and J. So nabla lambda stands for the squared eigenfunction.
So K energy only included the potential function mu in partial operator, no other parameters, lambda or the eigenfunction. So finally, we found K energy, those two Hamiltonian operators. Okay, so this is a very needful. Now, question: how do you produce the hierarchy, including Camassa-Holm equation, from those two operators? So the produce, of course, you need the source is to be taken from kernel J and kernel K. If you put kernel J, that is a regular soliton hierarchy in the positive direction. So in the past, many people work on the hierarchy, like PDV, MQD hierarchy in the positive direction. But most of people forgot the negative direction. So why we're interested in negative direction? Because Camassa-Holm equation, DB equation, would be come out from negative direction. So that is the idea, to study negative Camassa-Holm hierarchy. Now here, there's a L is a recursion operator. One of the things you need to figure out the inverse of this operator. The strategy to figure out the inverse of that operator, you need to find the product from that operator. Now you easily figure out the inverse of this operator. Okay? So after that, you get the L inverse. It's the inverse of a recursion operator. Why do we need that? Because in the negative direction, you have to have the inverse of the recursion operator. Now use this Nonlinear sequence to produce the whole hierarchy of the evolution equation. This is general scale. So also for negative and positive direction. Okay. Now negative hierarchy, which is corresponding to three seed functions. This is the, is generators to -1, generate negative hierarchy. One of the issue you have, this is the Camassa-Holm equation. Now people ask me, can we get more equation from hierarchy? Of course, you just go ahead to do next one. So I took special case, those linear combination coefficients for A1 is -1, other 0. You can also say that A2 is -1, other 2, and such. Now for positive hierarchy, you have this form, because this is a kernel, the recursion operator will produce the positive hierarchy. Okay, positive hierarchy, you have the typical members that's representative in the positive hierarchy. This is a Herdim type equation. If without the last term, this is typical standard the Herdim equation. This is why it's another importance for Camassa-Holm equation. Camassa-Holm hierarchy, the negative will produce the exactly Camassa-Holm equation. The positive direction is Herdim type equation. This is another important the equation in physics. Okay, that's a hierarchy. Now I'm going to show you integrability for the whole hierarchy. Now we are done today. So in order to get a Lux pair for the whole hierarchy, the key number 2, we need to figure out this solution of the matrix equation. What is given? U is given, energy are the Nonlinear operators already given. For arbitrary given the C infinity function G, the lambda is the eigenparameter. Now we need to solve for V. This is a matrix differential equation or differential matrix equation to figure out V. Usually that equation is overdetermined. U star is somehow a differential derivative for this matrix. Okay. Now 50 has the solution. Oh, I'm sorry, I should run second time not get a number here. So this is matrix equation 50 has a following solution. This is, of course, it's important to figure out all the Lux representation for the whole hierarchy. So this is the zero curvature equivalent to the Lux pair for the whole hierarchy. What is the Lux? What is the time part operator V sub k is defined by this. Now, so when positive, you take this summation. Negative, take this. The only thing is V sub j is the matrix solution for this matrix equation. Okay. After that, there's rewrite the Lux pair for the whole hierarchy. This negative hierarchy. This is the spatial part. This is the time part. For the whole CH hierarchy, it is integrable. Okay. Particularly for j equal -2, that's the Camassa-Holm equation Lux pair. It's a special case. Okay. Open problems. So integrability for high order Camassa-Holm models. High dimension Peakons I mentioned earlier, that we need to work on for future. So discrete Peakon system is nothing there. Still, we need to make development. Analysis for 2+1 dimensional Peakon system, we need to work on more detailed about analysis work. Okay, thank you so much. Here, last page show the Georgia conference. So I saw you have a session there. So hopefully we meet there to discuss more. Okay, that's my talk. Thank you so much.
Thank you.
Any questions?
I have one at the very beginning and one at the very, very end. Can you go back? Yeah, so when you're talking about multidimensional Peakon, do you mean line Peakons, or do you mean peaks that are peaked in all directions?
Okay, so multi-Peakon means, which means at least that number, capital number n, must be at least 2. Here, let me show you. That's the n is at least 2. That's called multi-Peakon. If n equals 1, just like I showed you earlier, this one. This is the one.
I'm talking about different things. So at the end, for open problems, you talk about multi-dimensional Peakons.
Oh, multi-dimensional Peakon. Okay, I'm sorry.
So do you mean line Peakons, like line solitons, or do you mean Peakons in all directions, like peaked in all directions?
Okay, so multi-dimensional Peakons, which means so you have to have an x, y, and t.
Yes.
Okay. So in that case, I think there's for x, both x and y in some direction. So the absolute value of that part you should include in. So not just x, something like a vector minus c1 was c1 c2. Somehow like the even velocity is vector as well times t. Now you put the absolute value somehow.
Okay, yeah. So there are line Peakons, I think, right?
Yes, correct. Yes, something like that. Line Peakon along the so velocity no longer is one single probably so the velocity is the vector.
Okay. Also about when you first wrote the Peakon formula for Camassa-Holm, you said that the C front, the multiplying C, had to be the same C that was in the exponent. But then you argued that you could get that solution by just solving f minus f double prime is equal to 0. That's a linear problem. Why do you need that form factor to be C?
Oh, I see. You are asking the single Peakon here, right?
Right there.
Right here, right?
Yeah. So 5 satisfies f minus f double prime is equal to 0, which would seem to solve the equation above it. Regardless of the value of C you put in front.
Right. That's a very, very good point, Bernardo. That's a C. This must be C, not any other constant.
Why?
Okay. Right. So, okay, Bernardo, let's do this way. Suppose here, note C, let's put A, capital A.
Yes.
You plug in that format. Excuse me. You plug in that format
into this equation.
Yes.
Finally, you're gonna take an integral, use test function. You will find that constant A must be equal, say, otherwise not zero right hand side.
So, so this specific problem that you deal with, because it is twice differentiable everywhere except at the point. So this is specifically coming from the singularity that you get from the F double prime.
Yes, right.
Okay.
Right.
So this comes out of this distributional considerations. Okay, got
Correct.
it. Thank you. Do we have any other questions?
Right.
Well, if there's no more questions, thank our speaker again.
Then plan to see you in April, Athens. Okay.
Absolutely. Thank you for your talk.
Okay.
Bye.
Bye-bye.
Bye.